Hi everyone and welcome to the webinar. Thank you so much for joining us today. Let's go ahead and get started. Today we will be discussing demand mode of operation. Low demand, high demand, what are you? My name is Loren Stewart. I work here at Exida with our mechanical customers, along with helping with certification and FMEDAs. I also do a lot of our research, whether it's on failure rates or 2H or stiction. Now, I know there's a lot of people on this webinar today that might be new. There's a lot of new names that I don't recognize, so welcome. And just in case you are new, I want to go ahead and tell you a little bit about exida itself. We were founded in 1999, and I like to say no matter where you are, where the people making your certified products are, where your customers are, we have someone close by to help with any functional safety need, whether that's in the process industries, alarm management, functional safety, or cybersecurity. And as I said, we can help with any of your functional safety needs throughout the complete supply chain. So if you're an OEM and you're making a certified device, or if you all the way through to the end users using the certified device, we have consulting, we have engineering tools, we have books, references, blogs, webinars to help get the information to you. In our consulting services, we not only have process safety or functional safety, why you might be here, but we also have alarm management and cybersecurity consulting services as well. We have engineering tools, and they were really designed to help save you time and money, and they do that because they increase your efficiency and productivity. So if you're trying to do PHAs, or LOPAs, SIL selections, or SIL verifications, or if you're doing cyber risk assessment or alarm rationalization, we have tools that can help you do your job easier. As well as our consulting services, we have certification services. You may or may not be familiar with exida certification. We have a lot of certifications that we've done in IEC 61508 and 511, but we also have certification in tool qualification, cyber, machinery, and personnel certification as well. But let's get into why you're here, the real reason you're here today for this webinar. Today we're going to be talking about demand mode, high demand, low demand, continuous mode of operations. In this webinar, we're going to start with some definitions, get on the same page on what a safety function is, what a CIF is, what we mean by low, high, and continuous demands modes of operations, as well as some examples of demand modes and CIFs. We're going to then look at the effects of demand modes on a system itself. We're then going to look at the actual SIL tables from IEC 61508 and 511. We're going to take a look at the differences between the high demand mode of operation and the low demand mode of operations, as well as some calculations. Throughout this webinar, if you have any questions, please feel free to use the questions tab. I'm going to make sure to save some time at the end of the webinar to answer any of them. So let's get started. To be able to correctly define low demand, high demand, and continuous demand mode of operation, we first need to define correctly what is a safety function and really functional safety. So a safety function is going to be a collection of different equipment. You're going to have your sensors, your logic solver, your final elements put together to implement automatic mitigation of a particular hazard. And those are two very important pieces of information. The safety function has to be automatically set into motion, and it needs to protect it against one particular hazard. The actual implementation of any single safety instrumented function is going to include one or multiple sensors or signaling condition modules, and also one or more sets of final elements. You can have your solenoids, valves, actuators put together. Also, depending if you are how your safety function is routed, how your application is, if you are an open on trip application and your safety function needs some sort of power or some sort of air to achieve its state, you also need to include the electrical power or instrument air in the definition of your safety function. With that said, we usually do not include any sorts of cables or terminal boxes in a SIF. However, at the same time, you still have to size them correctly, design them, and test them in good engineering practices methods. So when we look at what a safety function looks like, a safety function is apart from your normal control process. So your control process is highlighted here in green, whereas your safety function is in orange. So you're going to see you have your safety function, a separate safety function sensors, separate safety function logic solver, and separate safety function final elements. The functional safety standards, IEC 61508 and IEC 61511, both the old version and the new version of the standard, define modes of operation. However, the previous version of IEC 61511 and IEC 61508 had a disconnect in the nomenclature for the modes of operation. However, in the new edition of the standard, it was changed to match the definitions in IEC 61508 to eliminate some of that confusion that it introduced. With that being said, there are three different demand modes in operation: your low demand, your high demand, and your continuous demand mode of operations. In the process industries, in functional safety, most of the time we are talking about a low demand mode of operation. So we will be focusing a little bit more on low demand mode of operation, but we're still going to touch on continuous and high demand mode of operation. So what do those terms actually mean? Well, IEC 61508 and 511 have definitions for low demand and high and continuous demand mode of operation, but they were a little ambiguous. So exida took the definition from the standard and expanded it a little. So the exida definition of low demand is the average interval between the dangerous condition or that demand interval occurring infrequently, like for example, once per year. The automatic diagnostic test interval is an order of magnitude lower than that demand interval, and it is greater than twice the manual proof test interval. So breaking down, why are those things important? Well, if you have automatic diagnostics and you want to be able to take credit for those diagnostics, you want to be able to show that they are doing its job in finding errors. So you have to have the automatic diagnostics happening in order of magnitude more often. So say you have a demand, you're expecting your demand to occur once per year, the automatic diagnostics have to run at least 10 times per year to be that order of magnitude difference. And then your manual proof test. You want to do your manual proof test 2 times more often than your demand. And therefore, your manual proof test is still going to find some of those dangerous undetected failures. Continuous demand mode or high demand mode is when you have a frequency of your unwanted incident and it occurs more often. It is essentially going to determine your frequency of that demand. So when a SIF fails, the demand for action is going to occur in a shorter time frame than your proof test or your or even possibly your automatic diagnostics. So speaking of, if you have a failure and the probability of a failure, you never know when that's going to occur because your proof test is not going to find those errors because they're not going to be effective. So in high and continuous demand mode of operation, you're going to have the demand interval be less than twice the proof test interval. So what are some examples of safety function? There can be anything, really. Your car brakes is an example of a safety function. ESD valve, you're going to shut down a process fluid. A sprinkler system, a robot, a high pressure in a vessel opens a vent valve. What if you have speed sensing functions or guard sensing functions? Coolant valve could open, over sensing functions. There's all sorts of safety functions out there. The important part is that you have a group of equipment designed to protect against one particular hazard. There are different portions of the demand mode can be magnified if there are certain, sorry, I just lost my train of thought. So depending on which demand mode you are in, depends on which type of issues could creep into your devices in your safety function. So for example, you have a valve, a solenoid, and actuator. Well, what is something that can do to break your final elements? Well, you could have your valve be blocked. It could have a fracture. There could be parts in the valve or actuator that bind. You could have internal leaking. You can have a shear, chemical reaction, blockage, sticks, corrosion, cold welding, deflection, deposit buildup, external leak, lubrication breakdown, spring settling. There are all sorts of ways that final elements can break. And a lot of these issues in final elements can be exacerbated being in low demand mode of operation. Why is that? Well, if the valve or actuator in this example doesn't move often or stays in place for a length of time, extended length of time or more, some of these issues can be exponential, such as cold welding, or if you have deposit buildup. So in your low demand mode of applications, they can sometimes bring about more hazardous conditions or hazardous conditions more often because of the inactiveness of them, because of them not moving. So when you have something as a valve or a solenoid that's inactive for that long period of time, things like stiction can transpire. So knowing what type of mode you are in will really can really play a difference in how you treat your safety system. So what does the standard say? Well, for the different demand modes of operation, they have different rules, different tables, different calculations. So for example, you have a low demand mode of operation. IEC 61508 says you should use the PFDavg tables and the PFDavg calculations. And we're going to look at what those calculations and tables are coming up. But in a low demand mode of operation, the rule of thumb is you use the average probability of failure on demand mode of calculations and tables. With low demand mode of operation, you can take credit for proof testing and you can take credit for automatic diagnostics. Both of those are happening at relevant intervals that they will find dangerous conditions. So you can take credit for that. High demand mode of operation, instead of using your average probability of failure on demand, you use your probability of failures per hour or your PFH calculations. Along with those calculations, you're going to be using the PFH tables in the standards as well. And just like low demand mode, I'll show you what those calculations and tables are coming up. The main difference with high demand mode of operation is you can not take credit for proof testing, but as long as you are doing automatic diagnostics quick enough, you can still take credit for your automatic diagnostics. However, if you're in continuous demand mode of operation, once again, you're using the PFH tables and calculations. Once again, you cannot take credit for proof testing, just like in high demand mode. However, in continuous demand mode of operation, your automatic diagnostics are not going to be happening quick enough to catch any of your dangerous conditions. So you can no longer take credit for your automatic diagnostics. So this is what the one table for low demand mode of operation looks like. This is straight from IEC 61508 Part 1 of the standard table. And for those of you that are familiar with a safety integrity level, there are levels 1 through 4, and they're each in different order of magnitude. And this table relates the probability of failure on demand, or that PFDavg number, to a safety integrity level. And like I said, for each safety integrity level, there's an order of magnitude different in the PFDavg numbers. And we will look at how to calculate this coming up. This is the table for the high demand or continuous demand mode of operation. This is your PFH, or your probability of failures per hour. Same thing, there are still 4 levels. They still relate to the 4 safety integrity levels, and there's still different order of magnitudes difference between each safety integrity level. However, the numbers are quite different. When we talk about the average probability of failure on demand, we're talking about a long extended period of time. When we talk about PFH, it's a slice of 1 hour time periods. If you think back in calculus or pre-calc, when you learned about integrals, it's a slice of under the curve. It's just one slice of time. That's the same with your PFH. It's just one slice of hour. So the numbers are going to be much smaller. When we talk about PFDavg, so we're going to start off in low demand mode of operation, what the calculations look like. Well, as I just talked about integrals, well, in low demand mode of operation, the standard actually has integrals, but they also give you a way out. They said if you are talking about a single failure mode, low demand mode of operation, you can use simplified equations instead. And in the simplified equations, it's going to let you know that your dangerous failure rate, that lambda d, is very important, and your test interval is very important, and no other variables matter. Well, that might be well and good if you design a perfect system, but there are 9 key variables in case you did not design the perfect system, in case you are human and you do make mistakes. The extended PFDavg calculation takes into consideration, it still takes into consideration that failure rate and the test intervals. However, there's going to be some other variables included now, including initial failure, probability of initial failures, the redundancy of any devices, your mean time to restoration, the effectiveness of your proof testing, your mission time, whether you proof test with the process online or in bypass. If you are doing the proof test duration, if you are doing it in bypass, and the operation and maintenance capability, the end user's capability. So there are a lot of things to consider, but one of the most important variables in the PFDavg calculation is that proof testing. And because the proof test effectiveness and proof test interval can affect the PFDavg, but it can also affect the demand rate, I want to concentrate on that variable alone in this webinar. And because proof testing is such an important part of not only PFDavg calculations, but the demand mode, I want to take a moment and define just what a proof test is. And that may seem elementary or even redundant, but just like in the beginning, if we get off to the same definitions and talk about the same thing, it can really help understand exactly what we're talking about. So at Exida, we define proof testing a little different than the standard does. And once again, it's just because we took the standard definition and expanded it a little bit. So the standard defines proof testing as a manual periodic test performed to detect dangerous hidden failures in a safety-related system so that if necessary, a repair can restore the system to an as-new condition or as close to that as-new condition as possible. So Exida mostly agrees with that. However, they talk about the proof test being a test to detect any failures not detected by automatic online diagnostics. Whether those are those dangerous failures, diagnostic failures, parametric failures, and to detect any unauthorized program changes. And a big emphasis is on that automatic, not detected by automatic diagnostics. And that's because if your automatic diagnostics are doing their job, they're going to already find any dangerous conditions. So don't waste your time and waste your money retesting for those conditions, for those failures. What you instead want to do is run your automatic diagnostics, but when your proof tests comes time to do your proof tests, only look for things that were not already tested. When you are considering your proof testing and how do you make a proof test, the two main things you need to consider are your functional requirements and your performance requirements. So first and foremost, what does this safety function really need to do? Does the valve need to close or does it need to open? That sort of basic requirements. But then also you need to consider any performance requirements that might be important as well. Is there leakage? Are there any timing requirements? So for example, you might have a final element that's a close-on trip application, and the valve must close within 180 seconds, and it's allowed class 3 leakage. So that's saying that it needs to seal pretty well. It doesn't need to be a tight shut-off condition, but it still needs to seal, but it needs to do so within 180 seconds. When you are designing your proof test, one thing to note is all of the equipment that you are using, make sure you consult with their safety manuals. So if you're buying a certified product, you should have a safety manual of that product. And this will say any limitations or any exceptions to the rules that you need to consider when designing your proof testing. So a proof test means, I'm a visual person, so I like to see things graphically or visually. So what does a proof test mean? Well, as time goes on, your probability of failure is going to increase until you do a proof test. At that point, doing your proof test, you are either going to discover a failure or it's not going to be, you're not going to have a failure, or if you discover a failure, you will then restore it to an as new condition. So the probability of failing at that moment is going to be 0 because it either you know for a fact that it works or you restored it. So at that point, your probability of failure goes graphically. Let me get a laser pointer. So it increases the probability of failure until you do your test. And at that point, your probability of failure goes back to 0, so then you can start your test over again. So when you do your proof test, of course, you're going to try and do a perfect proof test. You're going to continue. You're going to continue up until you do your proof tests. You're going to do a perfect proof test, so you know the probability is going to continue down 0, and you're going to start that trend again for the lifetime or the mission time of your CIF. So when we talk about, especially in low demand mode of operation, we talk about your average probability of failure. So what does that mean? Well, your average probability of failure on demand comes into play at this portion because you don't know where in that spike, where in that curve you are going to fail. You're going to take the average of it and say, well, this is the chance you're going to fail in that time period. So why do I keep on saying perfect proof test? Well, if you run a proof test and you see the system respond, it works, what's the problem? Everything's tested, it's perfect, right? Well, it seems perfect to me. Well, is everything really tested? Let's say you do you look at a pressure sensor and you isolate it from a pump. or isolate it and pump it up so that your pressure is going to exceed your trip point. You have a remote actuated valve, and you can observe and notify that you see it moves. Everything's tested, right? Well, you didn't do a leak test, so you don't know if the valve seat is actually sealing properly. You didn't time it, so you didn't check your response time, so you don't know if something's having a lag or you're exceeding process safety time. You didn't check the process connections to the sensor. They could be failed. Your power supply, you could have issues with power supply or your diagnostic alarms. So there's a lot of issues that are built up that you are not testing. So even though you may strive to achieve a perfect proof test, many people do not actually achieve that. Let's say for another example, let's look at a butterfly valve. You have a pneumatic actuator, and it's a close-on trip function. You do a full stroke test of the valve actuator assembly. Is there anything you can think of that could be a dangerous, undetected failure after you do that full stroke test? Well, yes, you didn't check the seals or the butterfly or the shaft. You could have damaged seals. The butterfly itself could be damaged and let plenty of internal leaking. You could have a damaged shaft. It could be disconnected. So it depends on what you are actually doing your proof test on how perfect your proof testing is. So that's something that you really should be taking into consideration in your PFDavg calculation, is proof test effectiveness. And proof test effectiveness is going to be a percentage. It's going to be from 0 to 100. 100 if you test everything, you know you are perfect. 0 meaning you're not doing any testing at all. And your effectiveness is how much of those dangerous undetected failures you are actually finding. So what does that look like? And that's going to be added up throughout the lifetime of your product. So let's say you have a mission time of 4 proof test intervals. And whatever that proof test year is, a year, 2 years, 6 months, whatever that is. But you have 4 of them within your mission time. So for your first proof test interval, we're going to have a PFDavg about right here. The second proof test, because you're not returning to 0, your spike is going to start at a new location. So your second proof test, or your second proof test interval, your PFDavg is going to come out here. Same for your third and your fourth year, being the lifetime of this product. So yeah, your PFDavg increases. That's no big deal, right? Well, it might be, depending on how much it increases. Say this PFDavg, first one, you are falling in a SIL 3 application. You've done all of your calculations to a SIL 3, you're good to go, right? Well, what if year 2 or year 3, you fall to a SIL 2 range? What if year 4 you fall to a SIL 1 range? This, after time, could really add up to a lot. So when you talk about the PFDavg, you need to be considering the PFDavg not just for your test interval, but including the effectiveness, what your test interval might be for the lifetime of your SIF. What about, we've been talking about low demand mode of operation. Well, what about high demand mode of operation? What does it look like to run a high or a continuous demand? So let's say you have your same test, proof test, your same test effectiveness. your same test time period, what does it look like? Well, because your proof test isn't going to be necessarily effective because you don't know when your demand is happening, your demand might happen more often than your automatic diagnostics and your proof test interval, so your proof test won't be effective. That's why there are different calculations. That's why there's different tables for the different modes of operation. So all of that before was your PFDavg, your low demand mode of operation. Now we want to talk about your high demand mode of operation, or your PFH. With your PFDavg, it was your average over the long period of time, or your long test interval. However, your PFH is your probability of failure per hour. That's the shortest time period that you can take. Once again, it's for each SIL level, you're a different order of magnitude. However, the numbers for your PFH are much smaller. So instead of numbers of 10 to the negative 5, or your numbers instead of are 10 to the negative 9 and 10 to the negative 8, they're going to be more 10 to the negative 9 or 5 area or 7 area. So when we are talking about PFDH, there are two calculations you need to take into consideration. They're much easier and less complex than the PFDavg calculations. And they really come down to if your automatic diagnostics are effective or not. That's that order of magnitude difference, if they're running 10 times more likely than your demand or not. If they are effective, you can say your PFH is simply your undetected failure rates, your lambda DUs. However, if your automatic diagnostics are not effective, you cannot take credit for your automatic diagnostics. So your diagnostics are not finding those dangerous detected failures, so you need to have all of your dangerous detected and undetected for your failure rate. So in summary, we talked about what low, high, and continuous demands are, what safety functions are to start with, how proof testing can really affect your PFDavg and your PFH and your demand mode, and what the differences with the tables and the calculations are. So at this point, I'm going to go ahead and take some questions, and let me read them. Go ahead and read them if you have any questions. If you think of any questions later, I have a couple, but if you think of any later, please feel free to email me and I'll get back to them as soon as I can. And if you want more information, feel free to visit our website. We have books, white papers, blogs, webinars, lots of fun information on functional safety. And if you want lots of information, you can attend one of our trainings. We have week trainings, 3-day trainings on all sorts of standards. So feel free to look us up and go to our training. So let's go ahead and read some of these now. Thank you all very much for joining me today. And feel free to email me these specific questions and I will get back with you. Thank you very much.